Whoops! Once you've learned the algorithm for multiplication, you really haven't learned multiplication until you know the precision and accuracy of your answer. If I wanted to multiply a 5-digit number, which was truncated from a bigger number, I would like to know how accurate that answer is, or what the influence of the digits further down the line. So first I start off by multiplying 1, 2, 2, 2, 2 by itself, and then I add one digit. And I see that my answer, instead of being accurate to 5 places as the answer, it's only accurate to 4. However, if I add another digit further down the line, then I discover that it is accurate to 5 places. So I needed 2 digits to basically preserve those 5 places. And if I were to push it down another digit, I would see that I could get 6 places. This first 6 places would be accurate and not be influenced by that digit. And I tried this with other numbers just to see what the influence was in terms of round off. And so it came up with the conclusion that the formula to be safe is, in order to get it correct to the number of digits we see, which we'll call A, which would be 1, 2, 2, 2, 2, and B, which would be either the 9, the 09, or the 09, that if we take the lengths of those digits, the answer would be at least twice those digits, not considering round off. And then we would subtract the length of that first multiplication of the last digit by our original number, add 1 for possible round off, and then subtract these, and we'd get up that the answer would be good to the number of digits if we added 2 more digits. And so we gave a formula which basically would tell how many digits we'd need if we were going to multiply 4 numbers together. The next thing is to look at is, what about rounding? Because what happens, we're going to do a lot of multiplication, and we don't want to have to add lots and lots of digits. So I've taken a number, which is the square root of 10 to about 10 places, and I've multiplied it by the 4th root of 10, and I am looking at getting my answer accurate to 5 places. Okay, and so if I lop off at 3, round it off at 3, I do get my answer good to 5 places. If I truncate, I only get my answer good to 4 places. So truncating forces me to lose an answer. Okay, so next we look at what happens if we do lots and lots of multiplications to see about this round off, and or moving up to the next largest number if the trailing digit is greater 5 or greater. And what we're doing, we're trying to raise 1.01 to the 100th power. And we know from using a calculator or other methods that we'd like to see if we get the answer to 4 places just using no more than 4 digits. And so as we go down through the process, making use of the rules for exponents, we find that yes, we can get it good to 4 places with round off, which is nice to know, because if we were dealing with our computers and we could not take advantage of round off, we would never be able to get answers accurate to the full length of the computer for calculating certain functions. Okay, now we've talked about the errors that come due to just truncating our answer and trying to multiply it with that truncated answer and worrying about what the effects of the digits we threw away. But the other thing that we can have is we can make mistakes in our work. So what we're looking at is how we can check. One of the things to note is if we look at this function we're multiplying, here we're getting a step, no step, a step, and then a double step. And we'd like to know what causes that. And that has to basically do whether we round off, whether we have a carry digit on our last digit. If we do have a carry, then it depends upon what happens to the step before. If we had the step before was a no carry, then we would see it moving over 2 places. And a lot of times the problem we have is with the alignment of our numbers. We could also count the number of digits in the answer. This also has to do with the carry. So we look at 1, 2, 3, 4, 5, 5, 6, 7, 7 digits, and we have a carry, so we'll get the full 7 digits. If not, we'd have to subtract 1 and just get 6. And we look at the answer, 1, 2, 3, 4, 5, 6, 7 digits. Another thing we can do to check an answer is something called casting out nines. And this basically is adding up the digits, and wherever we get a 9 in our sum, we just toss it away. And we keep re-adding the digits until we're down to a single digit. So 42, casting out nines, ends up coming out to 6. And if we take the 5, 2, 2, 5, 6, and we round it off, we end up getting a set of nines with the first 3 digits. The last 5 and 6 is 11. Add the 11, 1 and 1, and we get 2. So we see here that 2 times 6 is 12. And when we add 1 and 2, we get 3. So the product, nines, casting out nines for the first, the multiplying the multiplicand, and then multiplying it, that's the number we're looking at, because the answer should have 3 in it when we do the same thing. And sure enough, when we add up the digits there, casting out nines, we also get 3. Another way of checking the work is by division. And we can actually divide 2 ways, as we see. The first way, we've marked an X out, because what we're doing is we're repeating the operations that we did before. And if we made a mistake in multiplication, then we would have made a mistake possibly again, because our mind may be in a rut on a certain multiplication. We might think that 6 times 8 is 42, for example, rather than 48. So we would make the same mistake, and we would not be able to catch the error. Okay, now the question is, if we do make mistakes, we'd like to be able to find them. Okay, and so what I've shown you in here is, usually when we make a mistake, the mistake is made in the addition, not in the multiplication. And what we see over here is that when we have done the multiplication, we can do a 3-digit multiplication at the beginning and a 2-digit at the end, and we at least get the leading and trailing digits. So most likely, if the error has been made, since the 15 agrees with the 15 and the 1, 2, 3, and the 25 agrees with that and the 45 times 45, then the most likely place in the error is between the 2 long red lines. Okay, and what happens is that's where we want to check our calculation. And we can see we've made the error in the worst place possible, where we had the most additions. But it turns out that the error in this case was caused by an error in the multiplication. The other kinds of errors are concerned about in measurements. We can't measure things exactly. Okay, and so every measurement has some kind of error associated with it. And we showed an algebraic technique for how we go about dealing with errors. So for example, we measured something that maybe was 5.23 inches long, and looking at our ruler, we may have decided that we think the error is good within 0.07 inches. We may have measured another line, since we might be measuring area, and that would be 27.1. And we think the error is about 0.3 of an inch. Okay, now when we multiply them together using the formula above, we get that the error would be 0.024. Okay, and what we found is we can add the percentage errors, and then that. So what we found is the errors are additive. We have to get them on a common base. We noticed that we approximated the error because as we went further out and did more of what was in the error, we would find that that's almost negligible. So now we find out that our answer is 141.733 plus or minus 3.4. Well, what we're really interested in is that where that 3 is, because that really talks about there, and that's in the integer portion of the additions. And so what we do is we only need to think good to 3 places, because the error is plus or minus 3, 0.7 is sort of somewhat irrelevant. We might have also considered rounding it up as one possibility. And in doing that, we might have a slightly more accurate answer. But we put down 141 plus or minus 4, and the 142, if we had rounded up, lies within there. The other way we could have also done it is to actually take the extreme limits. and you know, and take advantage of that, and we can see that that comes out consistent with the answer. So basically what we found out is if when we're doing our multiplication, we have to be very careful in terms of analyzing what the error is. And when one is doing scientific experiments and you want to measure things to a very high precision, you want to know that what the errors are, because that at least let you know how good your precision was. Thank you very much, and I hope you don't make any mistakes. Bye.